As I promised in the last video, this channel is going to expand to cover a variety of some really interesting technologies. And even though I'm going to continue to produce the laser videos for the time being and maybe forever, what I'm going to do is switch gears tonight, and I'm going to begin a series of videos about the construction, the design of a large carbon fiber multi-rotor. And to sort of orient the reason for this project is that multi-rotors have evolved a lot over the last few years. Racing drones and the consumer type of drones like the DJI Phantoms are pretty evolved, and they're easy to use, but because of their relatively low payload capacity and short duration of flight, there isn't a lot you can do beside aerial photography. But if you increase the capacity a lot and the duration substantially, you open up the possibility of using these devices for a much wider variety of purposes. If we can get good capacity payload, we can use these for transportation of cargo. We could use them for real agricultural spraying. They could elevate large antennas. Rather than carrying around a heavy mast, we could bring an antenna up into the air for both broadcast and reception. Also, these things could be used for inspections of buildings, pipelines, the environment, with mounting of large illumination systems. They can be used for search and rescue. They can be used also for applications even involving directed energy systems, directed energy weapons systems. And so in order to do that, you got to go big. And the controlling factor on the size and capacity of these devices is really the propeller. The larger the propeller, the greater the capacity of a multi-rotor to lift a certain payload for a given amount of power. And the larger the propeller, generally the larger the capacity, up to obviously certain limits. Well, one limit that we face here is that the largest available commercial propellers that are reasonable in price are about 30 inches in diameter. I got these from Hobby King, and pretty inexpensive. Dynamically, they're perfectly balanced, nice finish. They're carbon fiber, and at their 30-inch diameter, they pretty much define the size of the rotor that would, or the structure that would be necessary to support them. And in order to try to reduce the disk loading and take advantage of that efficiency, you want as many rotors as you can place on the craft. And practically that's 8 rotors, because commercial systems that are available to control them are limited to 8 rotors. So with 8 rotors, 30 inches in diameter, and a couple of inches of clearance between the rotors, you now have the dimensions of the device that you would end up building if you were sticking with these rotors. Because of that limitation, we looked at the possibility of going even bigger. And when you get any larger than this, you get to extremely rarefied propellers at extremely rarefied prices, where you would spend many thousands of dollars to outfit a rotor, multi-rotor like this, with just its propellers. Another video we're going to do in the near future is going to be our investigations in overcoming that limitation and investigating different kinds of rotor designs. Nevertheless, with the 30-inch rotors and the design and the dimensions, what we have to do then is decide, well, should we use 2, 4, 6, or use double motors and 2 rotors? And if you're looking for efficiency, the best system is a 2-rotor system. Primarily because when a propeller spins through the air, it produces turbulence. And so if you add additional rotors to a system, so that you produce a 4-blade propeller system here, and I've tested these, you lose efficiency, because the blade that follows the front blade has to work in the turbulent environment of the previous flow of the previous blades flow through the air. That turbulence reduces the efficiency of the blade, and as you add more blades, the efficiency continues to drop. It's pretty substantial. And even when you take the 2-motor systems, where you put a blade on top and a blade on the bottom, essentially you're still within the rotor wash and the disturbed environment, this disturbed airflow of the upper rotor, and the lower rotor works at a substantially lower efficiency. So again, if you want the best efficiency, stick with 2 rotors. There's another argument for getting away from the four-rotor design, and that is when these structures become as large as this and larger yet, the structure benefits a great deal from being able to articulate or bring the rotors in, as I have here. A two-rotor system makes that easy to do, but when you go to four rotors, you can't pack them together so well. And this unit, as large as it is when deployed, can actually be packed up in a very small package and put in the corner of a room like a potted plant. It gets out of the way and makes it convenient and easier to transport. Even these peripheral legs, which act to provide additional stability, can simply be removed by pulling a single pin out of the bracket. You pull the pin and you just drop that into a small bag and carry it with you. And in other words, and in that way, reduce the volume even more. The other sort of consideration when you're designing these rotors is what to use for the materials. And in aircraft, any kind of an aircraft, the only two materials that really should be considered are aluminum and composites. Aluminum has certain advantages, and that's why I use it for this one particular major component of the aircraft, which is the articulating bracket. And that is that aluminum is very easy to machine, it is very inexpensive, and it's also plastic or deformable, so it can be drilled and tapped for fittings, and that makes this very convenient for this application. But for the bulk of the rotor, the best way to do that is to use a composite. And other than price, you can't beat carbon fiber. Carbon fiber is extremely strong and extremely light and has the advantage of being able to be manipulated to actually enhance its performance in the direction that you need to use it. So as a result, you not only get that stiffness, but you get the stiffness in the way that you need it, and that further enhances the strength of the composite as opposed to, say, an isotropic material like the aluminum. As you can see here, I have a lot of carbon fiber. I've been working with it for years in constructing boats and airplanes. And everything I've used up to this point has been either vacuum bagged or hand laid up. But it essentially depends on carbon, which is a manufactured material that's generated out of a precursor called polyacrylonitrile. And it's a nylon appearing sort of a white plastic fiber that's generated in very fine, thin, hair-like fibers. And then the fibers are passed slowly through a furnace in a hydrogen environment, which realigns the carbon structure, creating a sort of hybrid of glassy and crystalline structure inside the carbon, substantially increasing its stiffness and its strength. And the carbon that comes out of it comes out in thin fibers which are then gathered together in what are called tows. The thing I'm holding in my hand is a 6K tow, which effectively means there's 6,000 fibers inside that little ribbon strip. The strip then is either woven into a two-dimensional array like this in the cloth, or it can be stitched together in a unidirectional array for very good unidirectional strength when building up larger structures. The problem, though, when you hand fabricate this, is that in order to express the strength or the quality of the fiber, you have to glue the fibers together. And in order to glue them, you have to use an adhesive. Epoxy is the most common. Polyester is rarely used. But the epoxy that you're bonding the fibers together with adds nothing to the strength of the material, nothing at all. It's the close approximation of the fibers and the shear of the epoxy adhesive that provides that bulk strength. When you hand lay it up, or when you lay it up with even vacuum bagging, you don't get the fibers as close as they possibly can. And that's why, in order to get the very strongest materials, the very stiffest materials, you really have to get it professionally prefabricated. The material I get is both from Rockwest Composites and from Dragon Plate, which are two U.S. manufacturers. And what makes their products superior is not only do they use high temperature cure epoxies, which are stronger and give you better shear strength, but also they do this in an autoclave. And an autoclave produces a lot of pressure during the curing process, squeezes the fibers together to get additional adherence, and also removes any of the dead weight epoxy so that you gain strength and lose weight. The end result is a material that is incredibly stiff. It's as strong as steel, as stiff as steel, and much, much lighter. And from this, you can then fabricate components that end up giving you the high performance of a carbon fiber structure. One of the things, though, to be concerned about whenever you're using very stiff, very high modulus materials is because they're stiff, they tend to be brittle. And what that does is it exposes you to some potential risk of failure due to point loading. Any fastener or any point where you're producing a substantial amount of force deforms the material that it's fastening to. And the deformation is actually a good thing, because what it does is it causes the stresses to spread out over a little larger area than the actual point is being loaded. And therefore you recruit strength from the surrounding material and limit the amount of actual force in that very small area, and you more closely approximate the bulk strength of the structure. So in this drone here, you'll notice I have what seem to be oversized bolts. The reason they're oversized is because of the fact that the larger hole that you see allows me to distribute the compression and shear loads over a larger area, which again defeats the point loading limitation. In addition, the carbon fiber at these points here, as well as where the motor is bolted through over here, are reinforced with doublers inside. There's actually additional epoxy material located in there. And what that does is it helps to reinforce the tube, which is otherwise extremely thin and stiff, but here thin and stiff and much stronger so that we don't end up fracturing it at those points. Another feature you'll see, I think you were filming that before, we'll look back at that, is that the plates that actually do the load handling and keep all of the arms oriented outward are constructed from the aluminum, which acts as the compression support, and an upper and a lower plate. And you'll notice the upper plate is thicker than the lower plate. That's because most thin materials tend to fail because of buckling rather than the material failure. And so because the upper plate is operating in compression as you're sort of upbending the rods, this plate is thicker, but because this lower plate is operating almost always in tension, it can be thinner and therefore lighter and retains the good strength of the overall structure. The bottom plate that holds the battery and the top plate that holds the control system can be quite thin because they don't have really much structural value, or you don't need their structural strength very much, so you can use a very thin, lightweight material. The other thing you'll also notice if we're at the hub here is an interesting feature is that these bars that come out of the brackets are not bored exactly in their centers. There's a slight offset. And the reason for that is it allows the arms to come off at a slight up angle called the dihedral. The dihedral is similar to what you see when you look at an airplane and the wings are not sticking straight out but tend to have sort of a V shape. And what this V shape does is it adds flight stability. And you can imagine why that would be. Because if the force vectors of the rotors are pushing out like this, what happens is when a perturbation or a wind or a gust tends to tip the device, the lower rotor, the rotor that moves more vertically, gains lift. It's actually aiming more down. And the rotor that was already tipped up is even more tipped up and loses some of its downward force. And so there's a correcting action that tends to keep the multi-rotor sort of the weight hanging in the middle of the V. The increase of, or the slight up angle does decrease the efficiency of lift a little bit because you're putting a little bit of that force outward, but the loss is very small and the gain in stability is pretty significant, and that's why you will see most drones and most airplanes having a dihedral. It also looks sexier too, so I kind of like that. The other thing that I would just mention here too is you'll notice that these tubes are square. You can obtain them in both round and square dimensions. The reason I selected square is because there are some mechanical advantages to a square tube. The stiffness of the tube is a high order of the diameter of the tube, or essentially the distance of the material from the neutral axis, or the line running down the center of the tube, whether it's round or square. A 1-inch square tube here and a 1-inch round tube have their materials located at different distances from the center. A round tube, it's at the radius. At a square tube, because of the corners, most of the material is farther out. So a square tube of the same cross-section as a round tube has about twice the stiffness, but only about 30% more material. So structurally, it's better. In addition, it's easier to work with because obviously the mounting bracket here works better with a square tube because of the clamping forces. They're being opposed by these upper and lower surfaces right across their breadth, and therefore there's no bending or bowing or ellipsizing that you would get from a tube. The same thing is true also at the motor end here. In most rotors you'll see, or multi-rotors you'll see with round tubes, a relatively heavy or somewhat weight-adding feature of sort of capturing this motor, which normally wants to mount to a flat surface, to a round tube means additional weight. There's another factor too to keep in mind, is that a square tube does have more aerodynamic resistance. And so a round tube is about half the aerodynamic distance as it moves sideways through the air. And in maybe a racing drone, that might be pretty significant because it's flying at like a 60-degree angle, almost like an airplane. But in these vehicles, which are almost always sliding laterally or slightly tipped, most of the airflow that's going past this aerodynamic blockade is coming from the rotor wash. But as we said, the rotor wash in these is relatively slow. And so the air resistance produced by a square versus a round profile should be quite small. This profile represents less than 2% of the disk area of the rotor. Later on, when we do the videos about the development of additional rotors, I'll also do some actual measurements of the support, and we'll see if in fact that does produce, as I suspect, a trivial amount of additional resistance, but we'll keep that for later. Another thing that I'll just sort of touch on here is the motor system. In using large diameter propellers but low power requirements, I've gone with these pancake motors because they have a very high torque. They have a large moment arm of motion, they have a lot of magnets, and they produce good torque, but they don't have to produce a lot of power. So they can be light and thin, but they have good torque capability, and that's why I've used these 100mm diameter pancake motors. Another interesting feature, and that's the property of running these motors through an ESC and from a power source, is that when we initially did a lot of tests, I've got probably a dozen motors, probably a couple dozen batteries, and about a half a dozen ESCs, is that we started out with a 6S and even an 8S system, which is a 25 volt or a 33 volt system. And I could produce lift thrusts out of the motors at down around 20% throttle. But the ESCs became quite hot. Even large ESCs, even with active cooling, they were still getting pretty warm. But when we limited the headroom on the rotors to about 70% of maximum throttle at hover thrust, the voltage drop from the batteries down to the motors was much less. The ESCs barely became warm. We could use smaller, lighter, cheaper ESCs. And as a result, the power efficiency became substantially better because we weren't just heating up the air with the ESCs. So this unit, despite its size, actually uses 4S batteries. We got a lot of amp hour capacity, but the 4S batteries are better matched to these motors, and that's a big advantage in terms of efficiency. One decision I made, and this is one you may not decide to follow if you do something like this, is I elected to not make the battery pack relatively easy to remove. We can take it off in 10 minutes, but it's not just a sort of snap it in, snap it out replacement if we want to do multiple flights. What I decided rather to do is to be able to charge all the batteries on board at the same time. So I actually have 3 dual chargers so that I can effectively charge all 6 batteries at the same time, and some elongated leads that allow me to do this, say, from a table or another surface, so I don't have to get in and get around the propellers when the chargers are charging. You may elect that it would be easier simply to have multiple battery packs, but that's a lot of batteries, and so I don't think you would necessarily save money. And that's just sort of a personal choice, and I wouldn't necessarily recommend it one way or another. So that's inherently what we're doing here with the multi-rotor. In the next video, what I plan to do is, or Alex will probably do, is we'll do the installation of the control system as well as the programming of the DJI A2 system that we selected for this multi-rotor. So hopefully that gives you an idea of what's going on here and maybe a little bit of information about how and why we construct carbon fiber multi-rotors like this. And in addition, this is just our first drone. I suspect if we have success with some of the rotor experiments, this may be just the first in a series of ever enlarging drones and capabilities. So I thank you very much for watching and hope you enjoyed it. Good night.